The intermediate value theorem and the mean value theorem are what are called existence theorems. They just say that something exists. There are some other existence theorems, and we're going to look at one, the extreme value theorem. This one is not used quite as much, but it's still a good one to know. If f of x is continuous on a closed interval, here we're back again to just continuous, but here the keyword is closed instead of continuous, a comma b, then f of x has both a minimum and a maximum on that interval. This is why it's called extreme value theorem, minimum being the lowest point, maximum being the highest point. However, there are very specific definitions for minimum and maximum, and they may be a little bit different than you might think. F of c is a maximum on the interval I if, so this is a maximum, f of c is less than or equal to f of x for all x in I. Notice that there is a little or equal to symbol. And we'll see in a graph in just a minute why that matters. Similarly, f of c is a minimum on the interval I if f of c, maximum should be greater than or equal to if f of c is less than or equal to f of x for all x in I. There we go. Note this only works continuous functions on a closed interval. So what this is saying, let's say we've got a little function like this, goes down like that. Here we've got a maximum, here we've got a minimum. However, if we have an open interval, there's no maximum. Basically, this open interval simply means that this single point is not defined, but we do have other points getting infinitely close to it, and since it gets infinitely close, we can't settle on a single number. We do still, however, have a minimum. Continuity also matters. Here our maximum is back, but let's say we have an open circle there. Discontinuous, no minimum. Still have the maximum up here though. There's also one that it might be a little bit counterintuitive. This is a constant function. All the points here are both minima and maximum, and the reason for that is because of this little equals sign that's under these two. Because this means that these are always true as long as we have that little equal sign, so that even in these situations there's still a maximum and minimum, it's just all points. Okay, let's look at some problems that combine all three. The function f of x is continuous on the interval 3 to 9 and differentiable on the interval 3 to 9. It's an open interval. F of 3 equals 1 and f of 9 equals negative 1. Must there exist a value c in the interval 3, 9 such that each of the following are true? So for the first problem, we're going to look at f of c equals 0. Does this have to be true? So pause the video for a second, look back at your notes, think about that, and start the video again when you have your answer. So f of c equals 0. We're talking about f, so we'll be looking at the intermediate or the extreme value theorems. We wouldn't be looking at the mean value theorem. So we know that f of 3 is greater than 0, f of 9 is less than 0. So as long as f of x is continuous, then there has to be a value for c, for x, such that f of c goes through all of the points between them. So since 0 is between negative 1 and 1, yes. Okay, for part B, does f prime of c have to equal negative 2? Think about that one for a little bit. So restart the video when you're ready. We're talking about f prime, so that means we're going to be talking about the mean value theorem. F of x is continuous and differentiable. So the mean value theorem applies. F of 9 minus f of 3 over 9 minus 3, that equals negative 1 minus positive 1 divided by 6 equals negative 2 divided by 6 equals negative 1/3. So no, the mean value theorem says there's a C such that f prime of C equals negative 1/3, but it says nothing about negative 2. And for part C, must there be a C such that f of C is less than or equal to f of x for all x on the closed interval 3 to 9. Okay, think about that one for a second. Restart the video when you're ready. Okay, this is talking about the extreme value theorem. F of x is continuous, so the extreme value theorem applies, and yes, there's got to be a minimum. That's just what the theorem states. Okay, for our last problems, we're just going to imagine something was different about these. This is 4. If f of x were not differentiable, in question 3, would A, B, and C still hold true? So remember, for part A, that was the intermediate value theorem, B was the mean value theorem, and C was the extreme value theorem. A and C, only require continuity, so they would still be true. B requires differentiability, so it would not hold true. I guess in this case, since we saw that this wasn't true to begin with, it's still not true. But really the key thing is that if we're going to work with the mean value theorem, we have to have differentiability. Similar note, if f of x were not continuous, would A, B, and C still hold true? And none of them would be. Continuity is required for all three.